Okay, good morning. So we've been talking about vectors and matrices and how we can use these two things to solve some real-world problems. Today, we're going to take things to the next level and thinking about how we can think about the long-term behavior of population models using matrices. So we're going to be talking about things called eigenvalues and eigenvectors. Can I have a show of hands who watched the pre-lecture material? Great, thank you very much. So this is the point where people maybe usually get a little bit thrown because eigenvalues and eigenvectors sound a little bit scary, but they're actually pretty straightforward. So essentially, what is an eigenvalue and eigenvector? Well, when we have a matrix, a square matrix, and we multiply it by a vector, we end up with another vector, right? So what is the relationship between those two vectors is what I want you to think about. So suppose we're in 2D and we've got a matrix A and we multiply it by some vector which has components, say, x1, x2. And we get something out that is y1, y2, okay? So we've just changed from some x's to some y's. Usually there's not really some relationship between those x's and those y's, right? We put something in, we get something different out, okay? And this is like a geometric representation is if we have our 2D plane and we have a vector that we start with, it's some arrow pointing from the origin to some point. We multiply it by our matrix and we get a different arrow. You know, it might be longer, might be shorter, might be pointed in a different direction, different angle, all of these things. And we do that for every single possible vector that we have in that plane. Now, eigenvectors are essentially just a special class of vectors where rather than changing the angle that we would have with the origin, we keep the same angle. So we either stay parallel or anti-parallel when we multiply a particular type of vector by this matrix. So every square matrix has a special class of vectors, which we call eigenvectors. Okay, so you can think about this a little bit geometrically here. Thinking about arrows coming from the origin, what happens when we take a vector here, for example, this u1, we multiply it by a, we get a different vector. u3 here, again, we take a vector, we multiply it by matrix, we get a different arrow coming out of it. Crucially here, if we take this u2 here and we multiply it by a, we get a vector that's longer, but it's still pointing in the same direction. It could be shorter, it could be flipped round. So it's got to be parallel or anti-parallel. This tells us that there's something special about U2. Okay, and why does that matter? Well, what matters is if you remember in our population models, so if we've got a population of juveniles and adults, say, we can represent the state of the population by a vector. What happens, what we care about often is what happens in the long term. Okay, so is this population going to grow? Is it going to shrink? What's the long-term distribution of juveniles to adults? Things like that. It turns out that as we keep multiplying a vector by a matrix, the whole population, this whole state gets pulled in the direction of what's our dominant eigenvector. So we don't have to multiply our initial population by 10,000 and do that for every different possible initial population. We could just take our matrix, look at the eigenvalues and the eigenvectors, and they'll tell us ultimately what is going to be happening in the long term. And this is true for these very simple population models, but also later in the course when we'll be talking about more complicated dynamical systems, whether they're models with infectious diseases or predator-prey or plant-pollinator, resource competition models. All of these models, we can tell something about their long-term behavior by looking at eigenvalues and eigenvectors that are associated with those systems. Okay, so it's really important that you get a good grasp of how we work with eigenvalues in particular, but also an understanding of what it is to be an eigenvector. So how do we actually go about calculating these things? Well, there's a bit of math in the pre-lecture talking about how we get to this point. The key things to remember really are this eigenvalue equation here. So we've got some matrix A multiplying it by some vector x, and we end up with some scalar lambda, some non-zero scalar lambda times by that x. Actually, lambda can be zero, actually, that's not true. So we have a scalar times by our vector x. This is our eigenvalue equation. What this means, we can do a little bit of rearranging here because we can multiply things by the identity matrix and not change anything. We can put an identity matrix in here. So now when we do that, we have a matrix here and we have a matrix here. That should be, make sure that's clear. Go back. We have a matrix here with this A, and we have a matrix here with this lambda I. We can take them over to the same side and factor out those matrices. So we end up with A minus lambda I times by our vector. Because we've done that, we know that we should have, we must have the 0 vector on this side. So what does that mean? Well, it means that if we try to invert A minus lambda I, then we're going to have ultimately x being equal to the 0 vector. But we started off with x as just being a particular vector, and we're going to assume that that vector is non-zero. So we've got a contradiction here. What does that mean? Well, it means that we can't take the inverse here. This inverse here does not exist. So that means that this matrix A minus lambda I must be singular. So what does it mean for a matrix to be singular? Well, it means that its determinant has to be equal to 0. So these lambdas here are going to be our eigenvalues. And when we take this, what's called its characteristic equations, we take the determinant of our matrix A minus our eigenvalues times by the identity matrix. We find the determinant of that new matrix. So just think of A minus lambda I as being a new matrix B, say. We find the determinant of that matrix, and it has to be equal to 0. So in a 2x2 system, we end up with a quadratic equation, and we can solve quadratic equations, right? So here in this particular example, we do our determinant of A minus lambda I. So this is our matrix A. This is our eigenvalue lambda that we don't know yet. And we have the identity matrix. We put those things together. And then we find the determinant. So we know how to define the determinant. We end up with a quadratic equation here. We solve our quadratic here. We can factor it. And we get 2 eigenvalues. Here, lambda 1 is equal to 4, lambda 2 is equal to -1. Doesn't matter which order we put these things in. We have 2 eigenvalues associated. Now, they might be repeated, but you always end up with 2. We'll talk a little bit later in this course about things with complex numbers. So they're not always real numbers. They can be complex numbers. But for now, we'll just focus on real numbers, okay? So we've got 4 and -1. So what does that mean? Well, it means that when I take our eigenvector that's associated with the eigenvalue 4, I multiply our matrix A by that eigenvector, and I get 4 times that eigenvector every time. Likewise, the second one, -1, there's a different eigenvector associated with this. So think of this as being there's 2 special directions here. And in that second special direction, if I take my matrix A, multiply it by that eigenvector associated with -1, I get -1 times by that eigenvector. Okay, so using this, we can find our eigenvectors because we know that our eigenvectors are going to satisfy this equation. You know that each eigenvalue has its own associated eigenvector. Okay. So we can solve this equation as well. Again, I'm not going to go into too much detail about this. Turns out there's actually a pretty simple way we can do this for 2x2 matrices. When you, for example, if we take this one at the top here, lambda 1 is equal to 4. This is an eigenvalue that's equal to 4 for this particular matrix A. What happens when we do A minus lambda I? So you do A minus 4 times by I, our identity matrix. We end up with a matrix here. And we know that this matrix is singular, right? Because we know that the determinant of this new matrix is 0. So that means that one row is a multiple of the other. You can actually do a little trick to find out or to immediately write down what our eigenvector is. We can take, for example, the first row. We can take this element here, and we change its sign, and we put it at the bottom of our eigenvector. We then take this element here and put it at the top. That's our eigenvector. Note that we can have any non-zero multiple of our eigenvectors. So there's an infinite number of eigenvectors that we can have. So this is just 1, 2, 3. I could have picked 4, 6, for example. That would also be an eigenvector. -2, -3 is also an eigenvector. So there is no unique answer here. They're only unique up to scalar multiplication, yes. Because we switch the sign. So the reason for this, the reason we can do this little trick is that if we multiplied out, let me do a different color. So if we multiply out this first equation here, so I'll do it in pink up at the top, we would get -3x plus 2y is equal to 0. Now, as I said, there's an infinite number of solutions, so I can pick a value of x or pick a value of y, and then the other one will be determined by that. If I take, change the color again, if I take this coefficient here and put that in front of my y value in my eigenvector and change the sign, and then if I take this coefficient here and put it in front of my x value, this equation is always going to be satisfied. Okay, so if I let x be, for example, if I let x be 2 and y be 3, I'm going to have -3 times by 2, which is -6, plus 2 times by 3, which is 6. So we have -6 plus 6, which is equal to 0. So this little trick with 2 by 2 matrices, we can immediately work out, and it doesn't matter if I took the top row or the bottom row from this a minus lambda I can immediately work out what my eigenvector is. Okay, so in this case, I wrote down 2, 3. Of course, it's not, I could have changed the sign in front of the 2, in which case I would have had -2, -3. Okay, remember that our eigenvectors are only unique up to non-zero scalar multiplication. Okay, so I can choose anything, think of it as being along a line, and I could choose any eigenvector that is along that line. So it could be very long, could be very short, could be pointed, either way. Okay, it's still an eigenvector. Okay, this is a little bit summarized here as to how we go about that. If you're not sure about that, just go back and check that in the pre-lecture material. Any questions about eigenvalues or eigenvectors before we start working through some problems? Okay. Okay, the first thing we're going to do is just check that we know how to verify eigenvectors. So here we're given two eigenvectors, v1, v2. We're told that these are eigenvectors for a matrix B, and we're asked to work out what our eigenvalues are. Okay, so remember, I'll write it in terms of B's here. What does it mean to have, for something to be an eigenvector? Well, it means that if we take B times by, say, v1, we are going to get some eigenvalue lambda1 times by v1. So to verify that this is indeed an eigenvector, we take b times by v1, so 2, 2, 1, 3, times by the vector 1, 1. So we end up with 2 plus 2, which is 4, 1 times by 1 plus 3 times by 1, again, which is 4. And then note that the vector on the right, the 4, 4, is just 4 times the vector on the left. So I could just rewrite this as 4 times by 1, 1. I've just taken out a factor of 4 from that vector. So now this vector is the same as this vector, just as we wanted here. We wanted this v1 to be the same as the v1 up here. And we found out this value here, 4, is going to be our eigenvalue. So in this case, lambda1 is equal to 4. How about the second one? Again, we do exactly the same thing. We take our matrix B, we multiply it now by this second eigenvector v2, so -2, 1. So you do -2 times by 2, we get -4 plus 2. So we get -2. And then we do -2 times by 1, so -2 plus 3 times by 1, so we get 1. Again, we have this vector on the left being a scalar multiple of the one on the right. In this case, it's just 1. I'm writing out here just so it's clear. we just have 1 times by that vector. Okay, so if we take our eigenvector minus 2, 1, we multiply by this matrix, we just get that same vector back again. So it's not moved at all. That means our second eigenvalue here is 1. So V1 and V2 are indeed eigenvectors. Yes? Exactly, yeah. So each matrix will have its own eigenvalues and eigenvectors. Okay, so they think of them as having a special match for that particular matrix. Okay. So we verified that V1 and V2 are indeed eigenvectors, and we found their eigenvalues lambda 1 and lambda 2. Remember that if you're finding, which we'll do in a moment, if we're finding eigenvalues and eigenvectors, it doesn't matter which one you label as lambda 1 or lambda 2. Okay, that's just a label. I could have said lambda 1 if I'd called this one here V2 and this one here V1, then I would have just switched the labels around. Okay, it doesn't matter the labeling. Okay, how about finding eigenvalues? So here we've got a matrix A, 3, 0, 0, 3. How do we find our eigenvalues? Well, we need to use our characteristic equation, which is finding the determinant of the matrix A minus lambda I, where I is the identity matrix and lambda are going to be our eigenvalues. Okay, so we don't know what those lambdas are at the moment, but let's work out what this is. So we're finding the determinant of a matrix given by 3 minus lambda, 0, 0, 3 minus lambda. So because I'm doing minus lambda I, I'm just taking away lambda on that main diagonal. So that's where those minus lambdas come from. So you take your original matrix and you just subtract lambda on that main diagonal, and that's the matrix you need to find the determinant for. Remember, because this is its characteristic equation, we talked about this matrix here, A minus lambda I, being singular. We know that this equation has to be set to 0. Its determinant is 0 because this matrix is singular. So how do we solve that? Okay, well, determinant of this is just going to be 3 minus lambda times by 3 minus lambda is equal to 0. Quadratic equation. In this case, we've got a repeated eigenvalue. We've got lambda 1 and lambda 2 are both equal to 3. Okay, let's do one more together. So let's do the determinant of B minus lambda I. So we've got a new matrix here. What's that going to look like, that matrix inside the brackets? Well, we're going to have 4 minus lambda, 2, 2, 1 minus lambda. And again, this has to be set to be equal to 0. So we find our quadratic equation by solving this equal to 0. So we find our determinant 4 minus lambda times 1 minus lambda minus 2 times by 2. And that has to be equal to 0. So that's just finding the determinant. Remember, when we're doing our determinant, we take the product of this main diagonal here and subtract the product of this off diagonal here. Okay, so we've got a quadratic equation. We can rewrite this one just by expanding it out as lambda squared minus 5 lambda is equal to 0. Which tells me that we have lambda times by lambda minus 5. If I factor out the lambda, that's to equal 0. So my eigenvalues are 0 and 5. And that's as easy as it is to solve, to find our eigenvalues of the matrix, okay? There's a couple more questions here. Okay, don't worry if you've not managed to write down the solutions. The solutions will be online. Have a go at finding the eigenvalues for these two matrices, okay? Okay, let's see how you guys got on. So, for the first one here, I'm just going to write down the solutions. The full work solutions will be online. Just check you guys got the right thing. You should have had lambda1 is equal to 3, lambda2 is equal to 1. Again, the labeling, if you did it 1 and 3, it doesn't matter. Those were your eigenvalues here. And in the second case, you should have had 1 and 2. Have a show of hands. Who got those right? Fantastic. Okay, so it's just as simple as finding the determinant and solving a quadratic. These ones, you could factor them, so it's all rather nice, but you might have to use more generally the quadratic formula to solve these things. Okay, finding eigenvectors. So I talked a bit before about how we can find the eigenvectors. I'm just going to run through this again just to make sure it's clear. Again, there's a full solution online. I actually use a different method in the solutions online to show you that you can do it by solving these equations, but there is this quick cheat method that we can do. So, okay, so we've got this matrix B here, and from above, we worked out that our eigenvalues were 0 and 5. Okay, so we've already worked this out. So what we need to do is we need to find the eigenvectors. We need to look at each of our eigenvalues in turn. So let's start off with lambda1 is equal to 0. What does that mean? Well, it means that when we take B times by the eigenvector, which I'm going to call V1, associated with lambda1 is equal to 0, well, we're going to have 0 times by V1. So this is just going to be the 0 vector in this case. So it would be 0 times by V1. Obviously, 0 times by anything is going to be 0. I'll leave that in there just so it's clear what's going on. So this means that we're going to have 4, 2, 2, 1. Times by, I'm going to call these x1 and y1 components. That's going to be equal to 0, 0. So that's what it means. Recall that we can do b minus lambda I. In this case, our lambdas are going to be 0, so we're just going to be having our matrix b minus lambda I. And the determinant of this must be equal to 0. So we know these things here. In order to get this, we can set our vector here as having the opposite sign for one of these coefficients and one of these rows. In fact, I'll do it with the second row here just to make it different. So I can take these two coefficients here for my x and y, switch them around, and change the sign of one of them. And the reason being, if I just get rid of this for a second, is if I multiply out this bottom row here, I'm going to have 2x1 plus y1 must equal 0. So if I switch those coefficients around, so I set x1 to be 1, and I set y1 to be, say, -2, so change the sign of one of them, then I have 2 times by 1 plus -2. And I have 2 minus 2, which is going to be equal to 0. So this is why this trick always works. Just put this in brackets here. So we can, in this case, use these coefficients here and switch the order around and change the sign of one of them. It doesn't matter which one I pick. I'm going to pick -2, just so I can. And as with many of the cases that we'll be doing here, if, for example, this is on an assignment or in an exam, how do I check that this is actually an eigenvector, that I've not made a mistake somewhere? How do I check? Exactly. So we have an equation up here that tells me what it must satisfy. So just go back and do the multiplication. So we have 4 times by 1 plus 2 times by -2. So 4 minus 4 equals 0. So because our eigenvalue is 0 here, we're going to end up with 0 on the right-hand side. Likewise, you can do it for the second component. So the good thing about a lot of the questions in this course is that you can go back and check that your answers are correct by just multiplying things out. Okay, so you can always go make sure that you have got the right answer We all make mistakes. We all make numerical mistakes all the time. I definitely do. And it's really good to be able to go back and check our working without having to just assume that we're right. Okay, so we've got another eigenvalue here. So let's go for lambda 2 is equal to 5. Again, remember what this means. This means that if we take b times by another eigenvector v2, we are going to get 5 times by v2. So let's this time look at our matrix b minus lambda 2i. What's that going to look like? Well, we're going to have 4 minus, we have lambda 2 times by the identity matrix. So we're going to do 5 times by 1, so just minus 5 here. We have 2, 2, so just the entries that we had in B. And then down here, we're going to have 1 minus 5 again. We have minus 1, 2, 2, minus 4. And note here that this row here is just a scalar multiple of this one. So if we times the first row of this matrix by minus 2, we get the second row. So whenever you have a matrix where, a square matrix where one of the rows is just a multiple of the other, that tells you that the determinant is going to be equal to 0. Okay, so using that, we can do the same trick as above. This time I'm going to pick the first row. So I'm going to pick this x and y here. I'm going to set my v2, my eigenvector, to be, I'll change the order of the x and y's, so 2 and 1, and change the sign of one of them. I'm going to change the sign of the minus 1, so it's positive. So I get my second eigenvector being v2 is 2, 1. Again, I could take any multiple of this, any non-zero multiple. So if I had picked, for example, I could pick 20, 10. I could pick minus 1, a half. Minus 1, minus half, I should say. So as long as we are, think of it as being a line, as long as we're staying on that line, we could pick a vector that is anywhere on that line that will still be an eigenvector. It's that direction that's special, not necessarily this particular value of v2. You might have a different value. Okay, as long as it's a non-zero scalar multiple of that, we're fine. Okay. What I want you guys to do is have a quick practice at finding the eigenvectors here using that method. So if we go back, what was the solution here? So we had 1 and 2 were our eigenvalues. So we'll start from that point. Lambda 1 is 1, lambda 2 is 2. Make sure I've got that correct. Yeah. Okay, so have a go at finding the eigenvectors for these. Okay. Again, in the online solutions, I actually worked through a different method to show it in more detail, but you can just switch the order of these things. In the interest of time, I'll just write down the solutions. You should have ended up with V1 being some non-zero scalar multiple of 1, 1. And your second eigenvector should have, again, been some non-zero scalar multiple of 2, 1. Can I have a show of hands who got those? Okay, who got those specific eigenvectors? Who got different eigenvectors but were scalar multiples of those? Okay, see, that's fine. As long as you got scalar multiples, that's okay. Okay. Very briefly, I won't go through this question here, but we've been working in 2 dimensions because we know how to work out the determinant of a 2x2 matrix. A little bit quiet, guys, thanks. So we know how to work out the determinant of 2x2 matrix, and that's all you're going to be expected. You're not going to have to work out the determinant of a 3x3 or anything bigger than that. But we can use the same principles to find and check that things are eigenvectors of larger matrices. Okay, so here in this case, we've got a 3x3 matrix, and we're told that these 3 vectors here are its eigenvectors, and you want to check that. The same equation that we had before works no matter how many dimensions we've got here. Okay, So you can find its eigenvalues by taking the matrix, multiply it by the eigenvector, and you should get some scalar multiple of that eigenvector if it is indeed an eigenvector. So you can do this one in your own time, multiply these things out and find the associated eigenvalues. Okay, I wanted to finish up today by going briefly through an example here of why our eigenvalues matter. In a very simple case, we can set up some sort of model of a real world problem. In this case, it's about a car share service and cars are being returned either to Burnaby or Surrey campuses. And from that, we can write down a linear system. Okay, so here I'm going to write down Sn for the number of cars on, I believe it's day n in Surrey, and Bn for Burnaby. Okay, so how do we work out what the number of cars are on the next day? Well, let's write down an equation for Burnaby. So on day n+1 in Burnaby, we're told that 2/3 of the cars taken from Burnaby are returned to Burnaby. So we have 2/3 from day n in Burnaby are going to be in day n+1 in Burnaby. And we're told that 2/3 from Surrey go to Burnaby as well. Likewise, we can write down an equation for Surrey. The next day, 1/3 of the cars from Burnaby go to Surrey. And 1/3 of them that start at Surrey stay at Surrey. So we've got some sort of model. We've looked at, it's very similar to our juvenile adult models that we've already talked about. This is just a model of a real world problem. We've got two unknowns. We can write this in matrix form. So I'm going to say a vector C n+1, day n+1. It's just going to be a vector composed of my Bn+1 and Sn+1. So this is just the distribution in Burnaby and Surrey. And then I can write this as a matrix equation just by taking the coefficients from the linear system above. So what are we going to have? We're going to have 2/3, 2/3 here. We're going to have our Bn and Sn. So the first equation, Bn+1 is 2/3 Bn plus 2/3 Sn. So if we multiply this out, this works. In the second equation, we have 1/3, 1/3. I'll refer to this matrix as A, and then of course we've got our Cn here. So we've written down a linear system here. I'll skip over the next part. So we can put a certain number of cars on day 1 and work out what is the distribution on day 2, day 3, and so on. But another way we can think about is thinking about the eigenvalues and eigenvectors. So let's find the eigenvalues and eigenvectors of our matrix A. So our matrix A was 2/3, 2/3, 1/3, 1/3. So let's find the determinant. I'll skip out writing the actual matrix here because it's just minus lambdas on the main diagonal. But our determinant of this matrix is going to be 2/3 minus lambda, 1/3 minus lambda multiplied together, and then minus 2/9. Remember, we're setting this equal to 0 because we're solving our characteristic equation. So we can do a bit of algebra to rearrange this and simplify it. You can just trust me that we end up with this. Lambda times by lambda minus 1 is equal to 0. Okay. So I know I'm skipping over steps here. Doing a bit of algebraic manipulation is something that if I do this in a lecture, I want you guys, if you're not sure about it, work through those steps in your own time. The solutions will often be a little bit more lengthy. I don't want to spend loads of time working through algebraic manipulation. I want you guys to think about the concepts, okay? So that's why sometimes I'll skip over some of these steps. So lambda times by lambda minus 1 is going to be equal to 0. So that tells me that one of my eigenvalues is 0, and the other one is going to be 1. So skip on to this page down here. What does this mean? Well, it means that if I I'm going to focus on this lambda 2 being equal to 1, okay, because this is the largest eigenvalue. And we'll talk more about the dominant eigenvalues for a system and what the relationship is with our solution. We'll talk about this more on Friday. I just wanted to introduce it today. So if we think about our second eigenvalue, lambda 2 is equal to 1, we can find our eigenvector that's associated with it. We do 2/3 minus 1, 2/3, third, and third minus 1, times by some, let's call it x2, y2, is going to be 1 times by, well, this is going to equal 0, sorry. So, again, I'm just doing a minus lambda I in this case. So, what do we have? We're going to have a minus a third, 2/3, third, and minus 2/3. Times by my x2, y2. It's going to be 0, 0. And write down my eigenvector straight away. I'm going to use this top row here. I'm going to change the sign of the one that's minus 1, minus the third. So flip them around. So I'm going to put 2/3 up here and a third down here. I'm changing the minus the third to a third. So this is my eigenvector that's associated with that eigenvalue lambda 2 being equal to 1. So this eigenvector written in this particular form here tells me, because this is the dominant eigenvector of the system, we'll talk more about dominant eigenvalue, sorry, this is the dominant eigenvalue of the system, we'll talk more about what it means for it to be a dominant eigenvalue. It tells me that in the long term, if I just let this play out, cars switching back and forth between Burnaby and Surrey, that the proportion is going to be determined in the long term of cars in Surrey, the cars in Burnaby, is going to be determined by this eigenvector. In this particular case, they happen to sum to 1. So I know that 2/3 of the cars are going to be in Burnaby and a third of the cars are going to be in Surrey. I could have written, just before you guys go, I could have written this as say 2, 1. This is also an eigenvector of the system. They don't sum to 1 now, right? But I can tell in this case that they're going to be in a ratio of 2 to 1. So you're going to have twice as many cars in Burnaby as there are in Surrey. So this eigenvector is really important, telling us about the long-term behavior of this system. We'll talk more about this on Friday. Okay, thanks.